Oh, Wheeler is here, okay. Oh, okay, I see you, Mr. Wheeler. Let me make a note of that. All right, so now we're in business. Let me share my screen. All right, so as I recall, and please correct me if I'm wrong, was this the last question that last thing we did last time? Oops, sorry. Did we do this example?
No.
No? Okay, let me back up a bit then.
That was,
I
I believe,
we looked at this?
we did. It's familiar.
Did we talk about mole fraction?
I think. It's, I think.
We did? All right. So, okay, so this is what we're gonna start off with today. So, this is based on the last law we looked at, which was Dalton's law of partial pressures. And just to remind you what that law is all about. Basically, that law deals with mixture of gases, right? So I'm just going to squeeze it up about here. That law says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases in the mixture. So the basis of this law is the assumption that in the mixture, each gas will exert a pressure, its own individual pressure, as if it's by itself in the container, all right? Okay, so let's look at this question. This question says the main component of dry air by volume are nitrogen, and it gives the percentage, oxygen, and it gives the percentage, argon, and carbon dioxide, and their percentages are given as well. So the question is asking, what's the partial pressure of each gas in the sample, or in a sample of air at 1.000 atmospheres, right? So these basically are percentages by volume, right? And because the number of moles is directly proportional to, or the percentage, or I should say the mole fraction, is basically based on this equation here, nRT, PV is equal to nRT. The number of moles is directly proportional to the volume, everything else being constant, right? So therefore, we can assume that these volume percentages would be the same as the mole fractions expressed as percentages, all right? So, remember we said that the pressure of a particular gas in a mixture will be equal to the mole fraction of that gas multiplied by the total pressure of that gaseous mixture, all right? So basically, to find, let me see here. Is there something missing? Oh, okay. So to find the partial pressure of each gas, right? We need to do a calculation for each gas for the mole fraction, which will be the same thing as the volume percentage here, multiplied by the total pressure, which is 1.00 atmosphere. So we're going to do the calculation for nitrogen, which will be equal to, now I'm going to express this as a decimal number, which will be 0.7808. That's the mole fraction, multiplied by the total pressure, which is 1.000 atmospheres. And that would be equal to 0.7808 atmospheres. And we do a similar calculation for the next gas, which is oxygen. So that would be 0.2095 multiplied again by 1.00 atmospheres equal to 0.2095 atmospheres. And then for argon, that would be 0.0093 times, again, 1.000 atmospheres. And this would be rounded off to 268, so that would be 0.0093 atmospheres. And then, so that's argon. And then the last one is for carbon dioxide. which has, okay, percentage wise is 0.004. So that would be the same thing as 0.0004 multiplied by 1.000 atmospheres. And that would be equal to 0.0004 atmospheres. And that's it. That's basically what the question is asking for. And you can do a quick check to make sure that this all adds up to 1 atmosphere. You know, just to make sure that your answer is at least valid, if not correct. So 0.7808 plus 0.2095 plus 0.0093 plus 0.0004, and that equals to 1.001, which is effectively 1 when rounded off to the correct number. Well, 1.0001, yeah, that's what I got when I add them up. So that's very close to 1, so that's fine. All right. Okay, any question about this particular example? Any questions? Any questions? All right, moving along. Let's talk about this situation of collecting gases over water. So in some cases where you're conducting an experiment and the experiment results in the formation of a gas, if you want to keep that gas, you have to collect it, of course, in some sort of container. Now, there are some gases that can be collected over water, right? These are gases that has very low solubility in water. So we're talking about gases like nitrogen, oxygen. That won't be true for fluorine or chlorine because those will react with water to form acid solutions. But hydrocarbon gases, right, such as methane, butane, well, not butane, butane is a liquid, but methane and propane, for example, or ethane, those gases can be collected over water because of their low solubility in water, right? So basically, we can have an arrangement such as what you see here on the screen, right? So what we have here on the screen is basically the apparatus for collecting water, for collecting a gas over water. And it consists of a trough, which is filled with water, and then there's a jar here, which will be previously filled with water. So basically, the way you'd arrange it is that you would fill the jar with water and then invert it into the trough, and therefore the water level will still be, well, the water will completely fill the jar while it's upside down in the trough, right? Now here we have a tube that is leading from some reaction vessel where the reaction is taking place, and it leads into the jar, as you can see here. So in this particular case, oxygen is the gas being produced, it's led into the jar, and what's going to happen, as I said before, is that oxygen has a low solubility in water. So therefore, eventually what's going to happen is that the bubbles of oxygen will lead to oxygen being collected over the water, and therefore that gas will exercise pressure, which forces the water level down. So if you continue to collect oxygen, the water level will go down. And what we try to do when we set up this experiment is that we allow enough oxygen to be collected until the water level inside the jar is at the same level as the water level outside the jar, right? The reason why we do that is because once we achieve that, we know that the barometric pressure acting on the surface of the water here would be equal to the total pressure that is exerted on the surface of the water here, right? And that makes it easier for us to do some calculation, right? Now, an important question is being asked here. The question is asked, what two gases are present here, right? And the answer is obviously one of them is oxygen, right? So the question becomes, what is the other one? And the answer is water vapor, right? Because if you have water trapped in any container, right? Let's say there's some space above it, right? In that space, you're going to have water vapor because you have this back and forth where the water vapor becomes liquid and vice versa, right? So eventually equilibrium will be achieved where you have a certain amount of water vapor collected right here. So basically there are two gases that will be present here. One would be the water vapor and the other one would be the gas that you'll be collecting, which in this case would be oxygen, right? So therefore we can write down a relationship between the barometric pressure, the water vapor pressure, and the pressure of the gas that is being collected, which in this case is oxygen, right? So basically, this is the relationship right here. In fact, what I'm going to do is write down that the barometric pressure, right, would be equal to the total pressure of the gases above the water in the jar, which would be the vapor pressure of water, right? Plus the pressure of the gas being collected, which in this case is oxygen. So therefore, if you want to find the pressure of the gas being collected, then that would be equal to the difference between the barometric pressure and the water vapor pressure, which is given right here, right? So that's basically how you will determine the pressure of the gas being collected. Now, the barometric pressure, of course, you can measure that. You know, we talked about the barometer before. So if you have an instrument in your lab, you can determine the barometric pressure. Now, the water vapor pressure, there are tables that actually has been published, which gives you the vapor pressure of water at different temperatures, right? So, in fact, I don't think I have that in my Canvas shell. So what I'm going to do today is that I'm going to see if I can find a copy of that table online, and I'm going to post it in Canvas because I think it's kind of important that you guys have it, especially when it comes to doing tests and so on, all right? So basically, if you want to find the vapor pressure of water, you would refer to those tables, and then the table usually has the temperature and the corresponding water vapor pressure. You just look at the water vapor pressure for this particular temperature of the experiment, and you plug that number into this equation, and the difference between those two would give the pressure of the gas that is collected above the water in the jar, all right? Okay, so here is an example of a question. Let me see here. Okay, I'm gonna need some space, so what I'm gonna do is copy and paste this onto a Word document. Try again. Okay, so this is a question here. Questions gives you an equation, and it says that the hydrogen gas that is produced in this reaction is collected in water at 22 degrees Celsius, when the barometric pressure is 742 torr. So the question is asking what volume of wet gas will be collected in the reaction of 1.5 grams of aluminum with excess HCl. So basically, you're going to start off with, in this case, you're going to start off with, in this case, 1.5 grams of the aluminum. So the first step in this process is to convert this to moles. So that would be 1 mole of aluminum above, and the molar mass of aluminum, which has, what's that, 26 point, is that 96? I can't see from here. Aluminum. AL.
9, 26.
26.9 what, 8?
8.
Okay, let's run it off to 26.98 grams, all right? So that's the first step, to convert from grams of aluminum to moles. The next step is, of course, determining the moles of hydrogen. So that means that we have to look at the mole ratio between the hydrogen and the aluminum. And based on the equation, which is balanced, you're going to have 3 moles of hydrogen above and 2 moles of aluminum below. And that will give you the moles of hydrogen produced in the reaction. So 1.5 times, or not times, divided by 26.98. And then I'm going to multiply that by 3 and divide by 2. And according to my calculations, this works out to be equal to 0.0834. That's what I got. Please let me know if I'm incorrect. But this is what I got for the moles of hydrogen, all right? Now, what the question is asking for is the volume of hydrogen, right? Now, based on the ideal gas equation, this is how you calculate the volume of any gas, including hydrogen, right? Now, a couple of things you're going to need. You're going to need the number of moles of hydrogen, which is what we just calculated here, right? You're also going to need the temperature, which is given here, but the temperature has to be converted to Kelvin, right? In fact, let me do that. So 273 plus 22, so 295 Kelvin, so let me just write this down. So T is equal to 295 Kelvin, right? Okay. We need R is a constant, R is always gonna be equal to 0.0821. So the question is, what is the pressure of the hydrogen gas, right? Now, the thing is, as in the experiment that I showed you before, the pressure of the hydrogen gas would be equal to the vapor pressure, would be equal to the total pressure or the barometric pressure minus the vapor pressure of water at 22 degrees, right? Now, they gave us the barometric pressure already, which is 742. So we have this here. What we do not have, and actually that should have been provided in this question, now that I'm looking at it. What should be provided to you is this, right? What I'm going to do right now is look up the vapor pressure of water at 22 degrees Celsius. So vapor pressure of water at 22 degrees Celsius. And let's see what this says. Would be 19.8 millimeters mercury or torr. So that would go here, 19.8 torr. And the barometric pressure is given as 742 torr. So this would give 742 minus 19.8. So this would give 722 torr, 722 torr. All right. So that would be the pressure that you're going to use here. So we plug in the numbers here. The number of moles of the gas is 0.0834 moles multiplied by R, which is always 0.0821 liters atmospheres over mole Kelvin. And then temperature, which is 295 Kelvin, divided by the pressure we just calculated, which is 722 torr. However, we cannot leave this as it is in terms of the torr units. We have to convert that to atmosphere. So we are going to multiply that by 1 atmosphere divided by 760 torr, right? So in terms of unit cancellations, the mole units will cancel out, the Kelvin units will cancel out, the atmosphere units will cancel out, and the torr units will cancel out. So the only unit remaining would be the liters unit. So let's do this calculation here. 0.0834 times 0.0821 times 295, and then divide that by 722 divided by 760. Okay, so according to my calculation, the answer I got is 2.13 liters. And that's how that is done. All right. Any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Excuse me. Okay, so let's continue our discussion with the PowerPoint. All right, so let's talk about the theory that is used to explain all the behaviors we have discussed, explains all the laws that we talked about in this chapter as it governs gases. It's called the kinetic molecular theory, all right? And I alluded to it earlier. Basically, that theory has some principal assumptions. Basically, that gases are made up of small particles. Those particles could be atoms or molecules, always moving. They're very highly energetic, and they move in constant random straight line motion. The second assumption here listed is that if you have a gas that is trapped in a container, then most of that gas is empty space, right? And that's because the particles are small and they are far apart from each other on average. Excuse me. Okay, another assumption is that there are no intermolecular forces between the molecule, right? In fact, the only forces that will exist is when they collide with each other. Apart from that, they move independently, right? And then the fourth assumption is that molecules may gain or lose energy when they collide, but the total amount of energy in that gas will be conserved, right? So basically, when you have two molecules colliding, there might be an exchange of energy. In fact, more than likely, there will be an exchange of energy, but the total energy between the molecules that when they collide would be the same. And the term that is used, I remember when I did physics, the term that is used is that these collisions are inelastic. Or I should say elastic, sorry, elastic collisions. All right. So basically, that's what the theory is all about. And based on this theory, we can explain the behavior of gases, why they obey Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, Dalton's law of partial pressure, and so on. So we're going to look at some qualitative aspects, right? Now, fortunately for you guys in this course, you don't need to memorize this equation, but I remember encountering this because I was a physics minor. So we kind of looked into this in more detail in our physics classes, right? Basically, this is the result of several calculations, right? You can actually determine a relationship between the pressure of a gas, N uppercase here, which represents the number of molecules, V represents the volume of the gas, M represents the mass of the gas, and then we have this term. This term here is basically the average of the squares of the speeds of the molecule, right? Let me explain what that means. Basically, what this term means, this will be equal to the square of the speed of gas molecule 1 plus the square of the speed of gas molecule 2 plus the square of the speed of gas molecule 3 and so on to the square of the speed of gas molecule n, all of that divided by the number of molecules, right? And that will be equal to this term, which is this term right here, right? So we call that the average of the squares of the speeds of molecules. All right. So that equation has been established based on a theoretical approach, and that equation was derived. And one important thing, or several things we can point out about this particular equation, is that it confirms some of our observations with respect to the behavior of gases. For example, if you recall, we said that the pressure of a gas is inversely proportional to the volume, right? That is Boyle's law. Well, that is clearly seen in this equation right here. Here's the pressure term, and here's the volume term. You can clearly see that the pressure is directly proportional to the inverse of the volume, right? Another thing I can point out here is the relationship between the pressure and the number of molecules, right? And this is predicted by Avogadro's law, which says that the pressure of a gas is directly proportional to the number of moles or the number of molecules. And here we can see clearly that everything else being the same, the pressure of a gas would be directly proportional to the number of molecules, right? Another thing that we can observe in this is that the pressure is directly proportional to the mass of the molecule, right? So you can make comparison between two separate gases, right? Let's say you're making a comparison between nitrogen and oxygen, right? Everything else being the same. The temperature is the same, the pressure is the same. The only difference is that we have these two gases, right? What you'd expect is that the pressure of the nitrogen would be greater compared to the pressure exerted by the hydrogen, right? And that's because nitrogen would be a heavier molecule compared to the hydrogen molecule. And then lastly, we can see that the pressure is directly proportional to the average speeds or square of the speeds of the molecules, right? So basically what this is saying is that the faster the molecules travel, the greater will be the pressure exerted by the gas. And we all know the reason for that. When the molecules travel at a fast speed, they hit the walls of the container more harder, and therefore the pressure exerted collectively by the gas particles will be higher as a result, all right? So you don't need to memorize this equation, but I thought it was important to show you so that you know that there is actually a relationship that you can establish between pressure and all these terms, right? Now there's another equation which I'm going to show you, which again you don't need to know. That is this equation right here, which relates the kinetic energy to a couple of things, mainly the temperature, right? The higher the temperature, the greater will be the kinetic energy, right? Now the R here is the molar gas constant, and Na here is Avogadro's number. So basically we have a constant divided by a constant multiplied by 3/2, which is another constant. So we can simplify this equation by writing it this way. And this EK here represents the average kinetic energy. So basically, what this equation is telling you is that the average kinetic energy of the gas is equal to a constant times temperature. So basically, there's a direct relationship between the temperature and the average kinetic energy. All right. So that's another equation you don't need to know, but you need to understand that there is a direct linear relationship between the temperature. And by the way, the temperature must be in Kelvin, right? I don't know if I stressed this earlier, but all the temperature values that you're going to use in any equation in this chapter must be expressed in Kelvin. All right, so that's as far as that is concerned. So let's move on to the next topic, which deals with the speeds of molecules. We touched on it earlier, but we're going to look at this in more detail. Molecular speeds, right? So of course, as you can imagine, if you have a gas in a container, not all of them, the molecules that is, not all the molecules will be moving at the same speed, right? Some will be slower, some will be faster, some will be fastest. So you have a broad range of possibilities in terms of the speeds at which a molecule will travel, right? So in order to identify, a number which represents the average speeds of molecule, we have what is called the root mean squared speed, right? The root mean squared speed is related to what we talked about earlier in terms of the average of the squares of the speeds of the molecules. So if you remember, I said, and I remind you here, that U squared average, that will be equal to the squared of the speed of gas molecule 1 plus the square of the speed of gas molecule 2 plus the square of the speed of gas molecule 3, and so on to the nth molecule, right? So, and by the way, divided by n, can't forget that, right? So all of this here represents the average of the squares of the speeds of the molecule, right? So it turns out that we can actually calculate that value here, actually the square root of that. So this here is here. What we're interested in is finding the root mean squared speed. That will be equal to the square root of the mean squared speed. And it turns out that this is equal to this equation right here, which is 3RT over M, all right? So just to identify the different terms, R is the molar gas constant. Now, if you remember, I showed you earlier in this chapter that I think I showed you 3 numerical values of R, right? And I said that one of them is 0.0821, and another one is 8.31 joules per mole Kelvin, right? Now, in this particular case, the R value that you're going to use is 8.31 joules per mole Kelvin, all right? So this is the R value that you're going to use right here, okay? So that's one important aspect of this equation that you need to be aware of, right? If you're using this equation to find the root mean squared speed of a gas, then you need to remember that the R value that you're going to use is 8.31 joules per mole Kelvin. Another thing you need to be aware of is the units for the molar mass that you're going to use. Now, in the case of the molar mass, normally the molar mass units would be grams per mole. That's what we've been using all along. In this case, however, you have to make sure that the units of molar mass will be kilograms per mole, all right? So in other words, whatever the molar mass that you would calculate, for a molecule, you need to divide that value by 1,000 in order to put that number into this equation to accurately calculate the root mean squared speed of a gas, right? So remember now, these two things you need to keep in mind if you're going to use this equation. The R value must be expressed as 8.31 joules per mole Kelvin, and whatever the molar mass that you calculate for the gas must be expressed in kilograms per mole, not grams per mole, kilograms per mole, all right? So once you get those, two things in order, put those numbers into the equation. And also again, as usual, temperature must be in Kelvin. So you put those numbers into the equation, whatever you calculate as a result of that, that would be the root mean squared speed, all right? And as stated here, these numbers or these values for the root mean squared speed are usually very high, in and around 1,000 meters per second. And based on this equation, again, we can see some relationships. The root mean squared speed, well, let's put it this way. As the temperature increases, the root mean squared speed increases, right? So let me just do that here. As the temperature increases, the root mean squared speed increases, right? We can see that according to this equation here. Another thing you should see here, based on the relationship between molar mass and the root mean squared speed, is that as the molar mass increases, the root mean squared speed decreases. So what this tells you is that for everything else being the same, if the molecule is heavier, then its root mean squared speed will be lower, right? So basically, lighter molecules will travel more quickly, heavier molecules will travel more slowly, all right? So that's what this last line is saying here. At a fixed temperature, molecules of higher mass will move more slowly than molecules of lower molecular mass. Okay, so that's as far as molecular speeds are concerned. So just to give you a more graphical representation of what we were just discussing, here we have a plot. Let me explain what's happening here. We have a plot of the relative number of molecules on the y-axis, and on the x-axis, we have the speed of the molecules, right? And these plots are for three different gases for this graph right here: oxygen, methane, and hydrogen, right? So if you remember, I said, if you have a gas trapped in a container, not all molecules will be moving at the same speed. Some will be slower, some will be faster, and so on, right? So what we're looking at here is the distribution of the speed of the gas molecules for oxygen, represented by this pink line. And then this line here, which I think is green in color, that's for methane. And then this is the distribution in the case of hydrogen, right? Now, how do we get the root mean squared speed from the graphs? What you have to do is look at the maximum point of the graph. So let's say we do that for oxygen, and we drop a vertical line, and where it cuts the x-axis, that would be the root mean squared speed. So, I don't know if I can do this accurately. If you drop a vertical line, okay, so what would be the root mean squared speed in the case of oxygen? This is 5,000, right? So this would be about what? I think it's about 4,000. All right. And then you do the same thing for the methane. Drop a vertical line down. Okay, so what do you think this is? So remember now, this is 500 here. This is 1,000 here, so this would be about what? About 700? Okay, I would say 700. All right. And then in the case of hydrogen, the maximum is almost at this point right here. So this is about what? 1,500, right? Okay. So these would be the root mean squared speeds of the different gases, right? And again, you're going to see the relationship between the molar mass and the root mean squared speed. In that, oxygen being the heavier, the molar mass of oxygen is about 32. The molar mass of methane is about 16. The molar mass of hydrogen is about 2, right? So of these three, the one that moves the slowest is the heaviest of the three, which would be the oxygen. Oxygen has a root mean squared speed of 400 meters per second. The next in line would be methane, which is 16 in terms of the molar mass. Its root mean squared is approximately 700. And then the last one is hydrogen. Its root mean squared is 1,500 meters per second, which is the fastest, which comes as no surprise because hydrogen has the lowest molar mass, right? So that's what's happening as far as the graph on the right is concerned. Now, let's look at the graph on the, graph on the left is what we just looked at. Let's look at the graph on the right. Now, in the case of the graph on the right, we have the same gas, oxygen, but the temperatures are different, right? So this is a distribution for oxygen when the temperature is 273. This is a distribution for the same gas when the temperature is 1,000, and this is a distribution in the case of temperature being 2,000 Kelvin, right? And what do we notice? The root mean squared speed will increase as the temperature increases as predicted by that equation. So in the case of the oxygen at 273 Kelvin, the temperature is, we saw that before, as 400 meters per second. In the case of the temperature at 1,000, let's see what this gives if you drop this down. This looks like about, I would say this is about 600. And then in the case of 2,000, the maximum is about here. That would be about, that's 1,000, that's 1,500. I'm gonna say this is 1,400, right? So we can clearly see in this case, as the temperature increases from 273 to 1,000 to 2,000, the root mean squared speed increases from 400 meters per second to 600 meters per second to 1,400 meters per second. So that is observed as predicted by the equation. As the temperature increases, the root mean squared speed of the gas molecules increases. Okay, so that's as far as molecular speeds are concerned. So the next thing we're going to talk about are two terms. One is diffusion, and the other one is diffusion. Now, I'm not going to spend too much time on diffusion, because what we're trying to look at is, okay, if you remember the equation I showed you, let me just write it here. Root mean squared speed is equal to the square root of 3RT over M, right? What we are going to look at is how we can look at certain factors that would be related to the root mean squared speed and see how it relates to the molar mass of the compound. So if we can find some way of measuring the root mean squared speed directly by experiment, we can see the correlation between the root mean squared speed and the molar mass. So one thing that was looked at in order to do that is to look at what is called diffusion of a gas in an experiment. So this is the definition of diffusion. Diffusion is a process by which one substance mixes with one or more other substances as a result of the translational motion of molecules. Now, if you try to use this equation to make predictions in terms of the diffusion of gases, what you'll find is that diffusion doesn't relate well to the equation that we have here. And the reasons why is because when you have two gases that are being mixed with each other, there'll be collision between the gas molecules, right? So basically, there's an interference that will take place in terms of the speeds of the gas molecules. So therefore, as a result, the speeds of molecules or the diffusion of molecules will be much slower than predicted by the molecular speeds due to the frequent collision, right? And there is a term here, the average distance a molecule travels between the collisions is called its mean free path. So because you have, collisions that occurring, you cannot use the root mean squared speed to make any prediction as to, for example, the molar mass of a gas, pretty much, right? So that's pretty much all we're going to talk about with respect to diffusion, right? What's more important in terms of using this equation is what is called effusion. Just realize. Okay, so before I get to effusion, let's talk about this interesting observation. So we have two liquids present in these two bottles, right? One of them is concentrated hydrochloric acid, and the other one is concentrated ammonium hydroxide, right? Very concentrated, so concentrated that if you were to open the bottles, you're going to see fumes of hydrochloric acid or hydrogen chloride coming from the hydrochloric acid bottle and ammonia coming from the ammonium hydroxide bottle, right? Now, these two gases will undergo a reaction where this gas, ammonia, will react with HCl to form a solid, which is ammonium chloride, right? So two gases will come together to form a solid, right? And what is observed in this setup here, if you open up the two bottles and allow the fumes to emit from the bottles, what you're going to find is that the ammonia and the hydrochloric acid will come in contact with each other and react to form the ammonium chloride. But the thing is, the ammonium chloride will be formed right here at the mouth of the hydrochloric acid, right? Now, based on what we have just discussed, can anybody explain why is it that the ammonium chloride will be formed close to the mouth of the hydrochloric acid bottle and not near the mouth of the ammonium hydroxide bottle? Can anybody suggest a reason why that happens? And you guys out there in Zoom, you can chip in with your response if you think you know what the answer is. Why is it that the ammonium chloride is formed at the mouth of the bottle containing the hydrochloric acid and nowhere near the mouth of the bottle containing the ammonia? Any ideas?
The mass of the HCl is higher
Okay,
than the hydrochloric acid.
right, well, no, higher than what? You're right, this is higher. Because this has a mass of about 30. Chlorine is what, 35.5 plus one, about 36. Okay, so the HCl has a mass of about 36. What's the mass of ammonia? Ammonia has a mass of about nitrogen is 14 plus 3, 17. All right, so these are the approximate masses. So you were saying what now? Repeat what you just said. You said the HCl has a heavier mass, right?
Yeah, so
Okay.
it's lower.
So therefore it moves slower. So therefore, when they come into contact, what's going to happen? They'll meet closer to the source of the HCl than the ammonia, right? And therefore, that's the reason why you see the ammonium chloride. You're going to see a smoky appearance. That's ammonium chloride that is formed at the mouth of the hydrochloric acid bottle, all right? So that's basically an explanation of that. I remember when I was in high school, my high school teacher did another experiment using these two same substances, but this time it was a tube, right? And the tubes were stuffed with cottons on both ends. One cotton would be soaked with ammonium hydroxide. The other cotton would be soaked with hydrochloric acid, right? So therefore, this will produce hydrogen chloride gas. This will produce ammonia gas. And you wait a while, and what will happen is that you're going to see a ring, a white solid ring formed at the end, closer to the HCl, the cotton soaked with the HCl, right? Again, for the same reason. The ammonia travels faster compared to the HCl, so therefore by the time they meet, they'll meet closer to where the HCl source is, and therefore the reaction will take place, and you're going to see, in this setup, you see a ring, a white ring of solid ammonium chloride form, all right? Okay, so I was about to talk about effusion. Oh, so that's the answer right there. Light ammonium molecules will move faster. And so, okay. So effusion is really what I want to get to, because effusion, we can actually relate the equation that I showed you to what happens in effusion. So first we have to define what we mean by this term. Effusion is a process where you have a gas escaping from a container through a very tiny hole into a vacuum, right? Now, in this case here, you don't have the problems of collisions as you would have in the case of diffusion, right? So here's an example here where you have a container here. You have two gases present, right? One is heavier than the other, right? You have a small hole right here. And then what will happen is that because the lighter molecules will effuse faster, they will escape from the hole at a faster rate. And if you allow that to happen for a while, what you'll notice is that the population of molecules within the container would be mostly the heavier molecules because they do not move as fast, right? So this can be related to the equation that I showed you earlier, which would be this equation right here. So if you were to compare two gas molecules or two gases in terms of their effusion, we can express the rate of the effusion of one gas molecule, or one gas, I should say, being equal to this term right here, for M1, for gas 1, and then for gas 2, this will be the expression right here. And if you were to do the appropriate cancellations and simplifications of the equation, this is what you're going to end up with, right? So you'll notice that there's an inverse square root relationship between the rate of effusion of a gas and the molar masses, right? And in fact, this can be stated in words, and this is actually known as Graham's law of effusion, which says that at a fixed temperature, the rate of effusion of gas molecules are inversely proportional to the square roots of their molar masses. And that's basically what this equation is saying mathematically, all right? Let me just say that I've actually seen in some textbooks where the term diffusion is used in the same way as diffusion, but please keep in mind that they're two different things, all right? Graham's law only applies to diffusion, and diffusion is what we talked about earlier, which does not work well when it comes to Graham's law, all right? So that's basically Graham's law of diffusion. And I think I have an example here where it says, if compared, by the way, what time is it? Okay. If compared under the same conditions, how much faster than helium does hydrogen diffuse through a tiny hole, right? So basically what you're doing is comparing the rates of diffusion of helium to that of hydrogen. So the first thing I'm going to write down is that the rate of diffusion of hydrogen divided by the rate of diffusion of helium is equal to the square root of the molar mass of helium divided by the molar mass of H2, right? That's the inverse square root relationship between these two gases, right? So what I'm going to do now is go to the periodic table and look up the molar mass of helium, which is 4.003. Square root of 4.003. And the molar mass of hydrogen would be 2 times 1.008, so that would be 2.016. So these would both be grams per mole. Grams per mole. And then we do the number crunching, so 4.003 divided by 2.016. And then I find the square root of that. And according to my calculation, when rounded off to 4 sig figs, that's going to be equal to 1.409. All right. So basically, the rate of diffusion of hydrogen divided by the rate of diffusion of helium is going to be 1.409. Remember now, the question is asking how much faster than helium does hydrogen diffuse? And the answer is H2 will diffuse 1.409 times faster than helium, right? And that's because of this expression right here, right? The rate of diffusion of hydrogen would be 1.409 times that of the rate of diffusion of helium, all right? So that's basically how that question would be answered, all right? Okay, any question about this? Any questions? Any questions? Any questions? Okay, moving along. Okay, now this one is a bit different. It says 1% of a measured amount of argon escapes through a tiny hole in 7.3 seconds. And then it says 1% of the same amount of an unknown gas escapes under the same conditions in 97.6 seconds. Calculate the molar mass of the unknown gas. All right, now in this case, they did not give you the rate of diffusion. They gave you the time it takes to diffuse, right? Those are two different things, but they're related to each other, right? I don't know if in your past experience you have looked at, for example, speeds of, if you have done anything in math or physics, where you're looking at the speed at which something travels, right? Or this rate at which something is done, some process, right? You should appreciate that there's an inverse relationship between how fast something occurs at the time. So if you have a process occurring at a faster rate, then the time taken for that process to take place would be smaller, right? There's an inverse relationship. So we can simply represent that relationship as the rate is inversely proportional to whatever the time is, right? Now, based on that, remember we said that the rate of, well, let's apply this to this particular question. We're comparing argon to an unknown gas, right? So I'm just going to say the rate of diffusion of the gas would be divided by the rate of diffusion of argon, and that would be equal to the square root of the molar mass of argon divided by the molar mass of the unknown gas, all right? So this is coming directly from Graham's law of diffusion, right? Now, based on what I'm saying here, we can also add another term on this side here, where the time of diffusion of argon divided by the time of infusion of the unknown gas would be equal to both of these two terms, right? So we do not need this anymore because we're given the times here, right? We're given the time for argon here. This is the time for argon, and this would be the time of infusion of the unknown gas, right? So now we have pretty much everything we need to calculate this, right? So I'm going to rearrange this equation to give the time of infusion of the unknown gas would be equal to the time of infusion of argon multiplied by the square root of the molar mass of the gas divided by the molar mass of argon, right? So this is what we get when we rearrange this part of the equation here to get the time of infusion of the gas. Oh, my bad. The question is not asking for the time, it's asking for the molar mass. So let me erase this here. I'm sorry about that. So what the question is asking for is this, all right? So my question to you is, how would you get rid of the square root sign? Let me see if you remember what you learned in math. You square both sides, right? So you're going to end up with M, the molar mass of argon divided by the molar mass of the unknown gas, and that would be equal to the time of infusion of argon divided by the time of infusion of the unknown gas, and all of that would be squared, right? What we need to find is this right here. So to get the molar mass of the gas, that would be equal to the molar mass of argon times the time of infusion of the gas divided by time of infusion of argon, and both of those would be squared. So put that there. So the molar mass of the gas would be equal to the molar mass of argon, which is 39.95. grams per mole multiplied by the time of infusion of the unknown gas, which is 97.6 seconds, and the time of infusion of the argon, which is 77.3 seconds. And we square all of that. So let's see what that gives. 39.95 times 97.6. Hold on, let me do the parentheses first. 97.6 divided by 77.3. Square that, and then I multiply by 39.95. And according to my calculation, this works out to be equal to 63.66. So 63.7 grams per mole. All right. So that's basically how that is done. And that answer makes sense because that means that the molar mass of the gas will be larger than that of argon because it takes a longer time to infuse. All right, so that's basically how that is done. All right. Any questions about this? Any questions? Questions? Okay, so let's talk about actually the very last topic in this chapter, the difference between real gases and ideal gases. So basically, all that we have done in this chapter, we were assumed that the gases are behaving ideal. And in actual fact, most gases under normal conditions, they tend to behave like ideal gases, right? However, real gases do not follow the same ideal gas law that we have been working with, and all the equations that we have derived basically are not followed by real gases, right? So there are two reasons for that, right? One of them is that in the case of real gases, there are intermolecular forces that exist, right? Ideal gases, we assume that each gas will act independently of, each gas molecule will act independently of each other. There are no intermolecular forces. So therefore, that's what happens in the case of ideal gases. However, in real gases, there are intermolecular forces that exist. That's one. The second reason why real gases do not obey the ideal gas law is that in the case of ideal gas laws, we assume that the particles, the molecules and atoms, have effectively a zero volume, right? We're assuming that in the case of ideal gases. In real gases, however, as you all know, the gas particles will have a non-zero volume value, even though that volume would be, of course, very small, all right? So what we can do, however, is that we can alter conditions of gases such that they will behave more and more like ideal gases. So the question now becomes, what are those two alterations you'd have to make, right? One of which is that the temperature would have to be very high in order for the real gas to behave like an ideal gas. If the temperature is low, then basically there'll be some difference between the behavior of real gases and ideal gases, right? Another thing you can do in order to make the real gas behave like an ideal gas is that the pressure would have to be low, all right? If the pressure is low, then what you'll observe is that the real gas will behave more like an ideal gas. If the pressure is too high, then there'll be, again, there's going to be some discrepancy between the behavior of real gases and ideal gases. So that's what is being, the point being made here, that under the conditions of low temperature and high pressure, real gases will behave less and less like ideal gases, right? Now, to demonstrate the effect of well, the difference between real gases and ideal gases when it comes to pressure exerted by the gas. We have these two situations here. The one on the left represents a model of how an ideal gas will behave in terms of the pressure exerted, and the one on the right is indicating how a non-ideal gas or a real gas will behave in terms of the molecules hitting the walls of the container. So, as we said before, in the case of real gases, well, let me deal with the ideal gases. In the case of ideal gases, the intermolecular forces don't exist, right? So each particle can behave independently. So when this particle is about to hit the wall of the container here, it will not be affected by the surrounding molecule, right? So therefore, this will hit the wall, and therefore that would translate into a certain value for the pressure exerted on the wall of the container. In this case, however, because of the attraction between this molecule about to hit the wall and these particles here, you have some attractive forces here. As a result of that, the force that this particle will exert when it hits the wall here will be lower compared to this one, and therefore, as a result, the pressure exerted would be low. All right, so that explains why, in the case of real gases, the pressure exerted will be less compared to that of ideal gases. Okay, and then so let's remind ourselves of the equation for ideal gases. PV is equal to nRT, right? We heard that before, right? Well, a guy by the name of Van der Waals, he examined real gases and he did some theoretical work. And as a result of his theoretical work, that resulted in a modification of the ideal gas equation. So this is called the Van der Waals equation for real gases, and that's the equation right here, right? Again, you don't need to memorize this equation. In fact, if I'm not mistaken, this equation is in the packet that I've posted in Canvas, right? But you'll notice that when you compare the ideal gas equation to the Van der Waals equation, there are some terms that were introduced. You have this term right here, whereas P was by itself here. In this case, you have to add this term to P, and then in the case of the volume here, which was by itself here, you have to add this term here to V, right? And these terms here, well, the N and the V would represent the number of moles and the volume respectively, but the A and B terms are specific to particular gases. A is a term which is related to the intermolecular force strength, and B is a term which is related to the volume of the gas molecules, all right? So those two terms, when you determine what those terms are, you can plug it into this equation and you can solve for whatever, all right? And I think the next slide, oh, and this is saying that A and B are terms that you can only determine by experiments, right? So you'd have to actually conduct some experiments on the gases to determine their respective A and B values. And the next slide, okay, I this out of order. Let me show you this one first, and then I'll show you the other one. So this slide here gives you the A and B terms, right, for different gases, right? So basically, these are the terms, the numbers that you use in the Van der Waals equation if you are asked to use it to solve for whatever, all right? Now, the last slide is the one that I just jumped over, shows you graphically how a gas behaves when you vary the temperature in terms of comparing it to an ideal gas, right? So remember now, the equation for an ideal gas is PV is equal to nRT, right? So in this particular case, we're talking about well, if I rearrange this, you're going to get N is equal to PV over RT, right? Now let's say the number of moles is equal to 1, right? Then that means that what you see here in the straight line here would represent the plot of PV over RT equals to 1, right? In other words, basically the pressure changes, but everything else will change such that it works out to 1 being the number of moles, right? So this is what happens in the case of an ideal gas, right? Now, if you take, and I don't remember which gas this is, because this is actually an experimental result, right? So for this particular gas, if you plot PV over RT versus the pressure, you're going to get this green line curve at 200 Kelvin, right? And then if you increase the temperature to 500 Kelvin, the shape of the curve looks like this, right? For the pink line. And then if you increase the temperature to 1000 Kelvin, then the blue line is what you're going to end up with, right? So if you notice, as the temperature increases, what happens? The curve flattens, right? It becomes more and more like the straight line, the ideal, right? So this is what is observed when you increase the temperature of a gas. It becomes more and more like the ideal gas. And the reason why is because as you increase the temperature, you're imparting more energy to the gas particles, and therefore the molecules or the particles will start acting more and more independently of each other, and therefore behave more and more like an ideal gas, all right? Okay, so that's basically it as far as this chapter is concerned. So based on what we have covered, you should now be able to do pretty much all the questions in the assignment. What time is it? Okay. Let me just see something here. So let me go here, here. And then just want to have a quick look at the question before I let you go. So let me see here. Okay. Okay. All right, so yes, you should be able to do all these questions. So what I'm going to do is I'm going to give you the chance to do these questions on your own. And then when we get back next week, Tuesday, if you have any questions about any of these, like, you know, maybe you encountered some difficulty trying to work them, we can deal with that in class. All right. So try these questions on your own. Also, you can also contact me during office hours. For example, I'll be here today from 2 to 5 today. If you have any questions, you want to come by, or if you want to do a Zoom link up, I'll be available for that as well. All right. So I won't set a deadline yet for submission of this assignment. I want you to try it on your own. And then on Tuesday, when we get together, we can discuss this, you know, whatever problems that you may encounter. All right. All right. So that's pretty much it for today, folks. And then we can start chapter 6 after that. All right. Okay. So that's it for today, folks. I'll see you guys next Tuesday. Oh, by the way, let me see who came in late, if anybody.
Martin.
Martin?
Yeah.
Okay. Let me see, anybody on in Zoom? I think I got everybody. Times. Medina. Oh, I didn't get Medina. Okay, so Medina is here. Let me see, the Rouge. E. So it goes,
Nice to meet you.
yeah, you do. And, Mr. Wheeler, okay, so done everybody, all right, so that's it for today, folks. And, for you guys out there in Zoom, I'll be signing off now.